Mechanics. Today, we are exploring the evolution of clutches, from primitive friction couplings to precision-engineered power transmission systems that connect the engine to the wheel. At its core, a clutch manages power transfer between a driving and a driven shaft through controlled friction. Three fundamental variables govern this interaction: the contact area, the clamping force, and the friction coefficient. A larger friction surface increases torque capacity, while the clamping force determines the grip strength, and the material pairing defines how effectively slip converts to engagement. In motion, a clutch performs three critical roles to protect the drivetrain. First, it enables smooth gear shifting by temporarily disconnecting the engine from the transmission. Second, it permits engine idling, allowing the engine to run while the vehicle remains stationary. Finally, it ensures a gradual load pickup, eliminating sudden torque shocks during startup. When looking at the types of clutches, positive contact clutches stand out because they lock driving and driven members using interlocking teeth or jaws. This purely mechanical connection ensures zero heat generation and immediate power transfer. However, because there is no friction-based slip phase, they can only be used at low speeds to prevent severe shock loading and mechanical damage. For manual transmissions, the single-plate dry friction clutch is the dominant architecture. Its effectiveness depends on the precise interaction of five key components: the release bearing, pressure plate, friction disc, flywheel, and the pilot bearing. The pilot bearing supports the input shaft, while splines on the disc hub allow axial movement during engagement, which is critical for smooth operation and heat management. Expanding the range of specialized engagement, we also see cone clutches and centrifugal clutches. Cone clutches exploit tapered geometry to multiply normal force, delivering higher torque in a compact package, a principle that lives on in modern synchronizer rings. Centrifugal clutches, on the other hand, use rotating weights and springs to engage automatically as engine RPM increases, requiring no pedal input, which makes them common in scooters and small engines. The way we control clutches has also evolved. Hydraulic actuation replaced old mechanical rods and cables, completely transforming clutch pedal feel and precision. When you press the pedal, force pressurizes fluid in the master cylinder, which transmits instantly through the hydraulic line to the slave cylinder. The slave cylinder then converts that hydraulic pressure into mechanical movement, pushing the release bearing to disengage the diaphragm spring and free the clutch disc. A major breakthrough in clutch design was the innovation of the diaphragm spring. By replacing an entire array of traditional coil springs with a single conical disc, engineers achieved a much more compact assembly. This innovation lowered pedal effort to reduce driver fatigue and provided consistent clamping force, which prevents hot spots and uneven wear. Looking ahead, the future of power transmission shows the clutch evolving from a driver-operated component to an intelligent, automated system. Modern automated systems, like dual-clutch transmissions, eliminate the pedal entirely and use electronic actuators for faster, smoother shifts. At the same time, advanced friction materials and cooling strategies continue to maximize thermal efficiency and durability. Whether manual or automated, the clutch remains central to mechanical precision and a testament to sound engineering fundamentals.